All right, let's get started. Hi, everybody. Welcome to our another round of our Fellows Lightning Talks. Up first is Dmytro Belytskyi.
Yes,
Dmytro,
I'm here. Hi.
you want to go ahead and share your screen?
Yes, of course. Second. Uh, can you see my screen?
Yes.
Good. So let's start.
Okay.
Okay, good. Um, can I start? Yes.
Yeah, go ahead.
Okay. I'm here to present. My name is Dmytro. My mentors are HL-LHC and Lenkaityte, and I'm here today to present our project, CMS Level 1 trigger scouting for luminosity measurement. Well, what is luminosity? And why it is important? Luminosity, as you can know, in the LHC, there is two contra-rotating beams which cross in certain points, and these points collision occurs. And the rate of this collision is related to such values, call it luminosity. This is very important thing because when we do some experiments to measure cross-section of one or another process, we normalize our data by this parameter. And so if we want to, so our data was legit, we should estimate luminosity with high precision. And yes, so how we measure it? For now, there is few dedicated modules to measure it. This is pixel luminosity telescope. This is beam condition monitor and a few other subdetectors like forward hadron calorimeter and fermion trackers. Well, this is good. This gives us some result, but the problem here is that at the phase 2, we expect much higher pile up to 200. Well, for now, it's about less than 100, and it will be maybe 2 or 3 times bigger. And the problem is that some parasitic effects like non-linearity, afterglow, and others, which give us error into our luminosity, they scale up very quickly. And to eliminate these effects, we want to do trigger one scouting. What is it? As you can know, the CMS detector give us a huge amount of data, and as we physically can process it in the real time, there is trigger which do decisions which data should be dropped and which will be saved. And this trigger is it introduces some bias into data, and as it data biased, it's unusable for luminosity measurement. Luckily, we have a system called L1 scouting, which not influenced by L1 trigger decisions, and it's safe few events, but at full rate of 40 megahertz, and this is likely to us. So what was done so far? So I set up environment in Docker container, CMS software environment. In this environment, I run a few scripts which convert objects. Yes, I forget to mention that this L1 system which saves objects from the trigger raw data, and so the script converts these raw objects into readable tuples, which could be processed with some conventional tools like payload. And in the next step, I write some Python scripts to process these tuples with pyroot, matplotlib, and other libraries. This data is basically some observables, which is we derive from detector at full 40 megahertz rate. Well, as you can see in this picture, there is a compensator per bunch. Yes. So I built some histograms, which is, show us how we could do initial cuts to reduce signal to noise ratio. And the next step, what we will do, we compare this data to the actual luminosity, and we try to estimate which is of observables is linear to luminosity, and which of observables could be used to relate what objects we get from the detector to the actual luminosity. And then we do some Monte Carlo simulation to verify that our estimations are correct. And this is it. Thank you for your attention.
Thank you, Dmytro. Any questions for Dmytro? All right, thanks again. Up next is Vladyslav.
Yeah, hi.
Hi.
Give me a second, please.
Sure.
So you can see my screen, yeah?
Yep, go ahead.
Yeah, okay. So, hi everyone. I am Vladyslav Yankovskyi, a master student at the Russian International University of Kiev. My mentor is Andrei Usachov from NICHEV, and my project is devoted to development, the displaced vertex finder or GE finder on GPU for LHCb. So, briefly about the motivation of this work. Many new physics scenarios that exist now posit the existence of new long-lived particles that could help explain long-standing puzzles in physics, such as the original of dark matter, for example. Such particle can be produced in high-energy proton collisions at the Large Hadron Collider and can be detected by the LHCb detector. But to do this effectively, we require a special algorithm that can quickly identify the so-called displaced vertices where these particles appear. And then when this algorithm will be developed, it will need a fast CUDA implementation to run online on a LHCb GPU farm. And so the main goal of this project is to find this displaced multi-track vertices with anomalous topologies. So let's talk about the software I work with. This is the HL-LHC or high-level triggers. What is this? Currently, the LHCb detector is capable of reading out a maximum data rate of 40 terabits per second. This is a huge amount of data that needs to be filtered, which is achieved by these two software stages, HLT1 and HLT2. In LHC run 3, HLT1 was improved by implementing it on a GPU. It's the first fully GPU-based trigger which used in HEP, and this allows us for parallel event processing using the Allen application, on which the algorithm my algorithm GFinder will run. Okay, there you can see the design of the LHCb. And now we are interested in a first detector. It's a value detector. And there is a figure shows the design of half of the value detector. There you can see the 21 models, each contain of 2 sensors, the azimuthal and radial coordinates, and the zeta coordinates we determined as a position of the models. There we can see the scheme of the near interaction region, where we can see that most tracks, most valid tracks associated with primary vertices, it's about 80%. So look closer what we have in this region. There we can see a huge number of valid tracks, and we can use them for reconstruct the decay vertices. For this work, we can distinguish 2 main types of vertices. It's primary vertices and generic displaced vertices, GDV. PVS are located close to the beamline, and to the beamline. Beamline it's a tube where particles accelerate. And this PVS we can consider as a point of interaction of these protons in the collider or decay of short-lived particles. But GDVs are located at the distance from the beamline, and we can consider them as a candidate for LLPs, decay vertices. So in the previous IRIS-HEP Fellows Program 2024, an algorithm with the main stages of building this GDV was implemented, and I want to shortly describe how it works. So the first stage, we compare every 2 tracks in the event, and if they are close enough according to the chi-square criterion, we build a so-called seed vertex, which is a future candidate for the real vertex. After that, we check if there are any other tracks that also belong to this vertex, depending the distance between them and also the chi-square criterion, and add these tracks to this vertex. And after that, we have a set with a large number of vertices. And there we can see that we can see the group of vertices, which is close enough that we can treat them like one vertex. So we need to merge this vertex on this merge stage. And after that, we have a set of this GGV. Okay, what we want to do on this? What our missions for this program? So to further improve the efficiency of reconstruction displaced vertices, it's necessary to add the calculation of the errors, and it's calculated in form of the covariance matrix. So also it's important to define the criterion displacement for the vertex and the corresponding constraints on the parameters of these vertices, like coordinates, distance to the beamline, and number of the tracks, and so on. Also, it's important to investigate the optimal parameters for the all stages of this algorithm, like our constraint for chi-square criterion, where we can consider 2 vertices as one, and so on. And once this algorithm will be ready, it will need a fast coding implementation to run online on this LHCb GPU farm. It can be done using ALIN, which is the HL-1 application what I talked before. This ALIN will allow us running the algorithm on both the CPU and GPU. And of course, at the end, we need to test algorithm on the Monte Carlo simulations using the standard model and beyond standard model physics that can generate these displaced vertices. So, okay, it's all it worked. Thank you for attention. You're free to ask any questions.
All right, thank you, Vladyslav. Any questions for Vladyslav? No? All right, thank you. Next up is Danylo.
Okay. Can I share my screen?
Sure, go right ahead.
Okay. Can you see my screen now?
Yep, you're all set.
So, hello everyone. I am Kulakov Danylo. I am from Taras Shevchenko National University of Kiev. I am just at master degree. And so my project is DevOps in a cloud-hosted database for high luminosity LHC FBCM detector development. So introduction. First of all, you can see here where this detector will be. It's beamline. And this detector consists from two parts, half disks. Each half disk have different DC modules, ASICs, and detectors, and so on. Different parts of detector will be produced in this or next year and will be assembled in 2028. So we need to store all information about the tests on these ASICs and other sensors. People should have an ability to store this data for a long time. Okay, so my task in IRIS-HEP project is to make that cloud-hosted storage for all these parts of detector. I'm working in Django framework and using PostgreSQL database. So as you can see, here we have a half disk, and I marked here what is ASICs and where we have actual sensors. We call it 6 pads or 2 pads. And so each part of this detector have its own tests. We need to check different voltage or capacitive characteristics. Also to check before irradiation and after irradiation. We have to build different plots, histograms to compare different models with each other. And it's my task to make it simple to use and user-friendly. So current progress, I am just working 1 month, and for this 1 month, I running this database locally. In future, we will put it on CERN servers. So now I finished sensors, 2 parts, 6 pads, and ASICs data page. I implemented comment editor, and also I implemented that we can see different connections between each sensor. And my future steps, I need to think how to make it more user-friendly, ask our team what they will need in future. So that's not only about comparison of different characteristics of detectors, but also for editing and checking if all parameters was or were in normal conditions. So also I need to review the data logic in relation to other components such as hybrids with ASICs and sensors, components on the HAL disks. And also it's a very important task to debug our database. And to be sure that when we will put it on online operation mode, it will show us the proper way to work. And also, I forgot to notice that I started to write a manual for this database. And it's also my main task to develop not only database and also develop manual how to use it, and maybe how to add more features, so on. And that's all.
Thank you, Kulakov. Any questions? No? All right, thank you. Next up is Luka.
Yes, good evening.
Hello.
So I'm gonna share my screen just a second.
Okay.
Oh. Hello once more, everyone. My name is Gavrysh Luka. I'm a fourth-year bachelor student at Taras Shevchenko National University of Kyiv. I'm currently working at the CMS experiment in the Boston University group under the supervision of Serhiy Cholak. And my project is software development for the inner tracker data trigger and control system. So let's begin a bit more about the inner tracker. The LHC is being upgraded for its high luminosity phase, as you might know. And the CMS detector is being improved as well. The new detector system is divided into two parts, the inner and outer trackers. And the inner tracker is designed to perform under the extreme conditions, including pile-up to 200 collisions per bunch crossing, extreme radiation levels around 1.2 grad TDI, and the heat rates exceeding 3 gigahertz per centimeter squared. So to the right, you might see the inner tracker structure that consists of 4 barrel layers or TB peaks that surround the beamline with a fine granularity. 8 forward disks, TF peaks that are mounted perpendicular to the BM axis, capturing the forward region particles, and 4 extension disks or TE peaks, which extend the coverage into the even more forward regions. The 1/4 of the slice representation, this geometry is visible as a quadrant of concernic and radial pixels layers that together make up a fully cylindrical detector volume. In the inner tracker, it's gonna be used the pixel modules, the pixel detectors. Each module contains a silicon pixel sensor with 2 pixel types and sizes. One of them is a square, 50 times 50 micrometers squared, and the other one is rectangular. It's 25 times 100 micrometers squared. And sensors It can be two types, as I said, planar or 3D. And 3D variant is used in the innermost layers due to its superior radiation hardness. Also, each pixel sensor is bound to a readout ASIC, RD53 chip. There are two types, A and B, which digitalize the process, the heat information directly to the module, but we're going to talk a bit more later about it. So as I'm working on a software project, I need to tell about more about the inner tracker hardware. The main component of it is Apollo board, named by the first humanity space mission Apollo. Apollo is the modular ATCA blade, or Advanced Telecommunications Computing Architecture blade, that is designed as the backend data acquisition and control system for the CMS inner tracker. It serves the interface between the front-end pixel modules and the central CMS DAQ and level 1 trigger system. It's divided to the two parts: the common module that is made by the Cornell University. It's a module that equipped with two FPGA boards. You can see the photo of the Apollo to the right. Also, the common module handles the high-speed optical data from the low-power gigabit transceiver or LPGBT links that supports up to 72 LPGBT inputs for 10 gigabits per second each, 16 high-speed links to the central DAQ. Each one is 25 gigabits per second, and from 4 to 8 high-speed links dedicated to Brill and level 1 trigger system, as well as the common module has a real-time data processing and formatting. And the other one part of the Apollo board is the service module. This module is being developed by the Boston University. It's a Linux-based embedded system that is running on a Thing. It manages the distribution, clocking, slow control, and communication via Ethernet protocol. So the module that is being as a part of the detector is the readout chip, RD53, as I said. You may see the picture, the small schematic picture of it to the left. It's a radiation hard readout ASICs that is specifically developed for pixel detectors for high luminosity LHC experiments like CMS and Atlas. They're implemented in the 65 nanometers SMOS technology to achieve the necessary granularity, speed, and robustness. So each readout chip has for CMS a matrix from 432 times 336 pixels each. So now we can talk a bit more about the data chain that we get. First of all, the readout chip detects the charged particle, hits on the sensor, amplifies the signal, and digitalizes it. Then it performs zero suppression, keeping only relevant hit data, and the data are transmitted via high-speed serial lanes to the LPGBT ASIC. LPGBT aggregates up to 3 readout chip streams and send them optically to Apollo. Apollo's common module receives this data, performs packet parsing, event building, and either stores or forward it to the queue and trigger logics. So during last months, I've been working with other type of hardware. As I said, it's a low power gigabit transceiver, but as well as the readout chip and Apollo are used into my task right now. So now a bit more about the low power gigabit transceiver or LPGBT. It's a kind of communication bridge between the front-end electronics, in our case is a readout chip, and the backend systems, in our case it's Apollo, aggregating data from up to 3 electrical E-links and sending them via a single optical uplink at 10 gigabits per second. In addition to the data transmission, LPGBT has a distribution of distributes clock and trigger signals, handles fast control, and supports slow control of front-end components. What have I done during the previous months? As the part of CMS Phase 2 Inner Tracker project, I've currently developing a link mapper tool that dynamically reads the mapping between LPGBT links and detector modules directly from the firmware registers. This avoids the need to hard-code configuration, so it's just avoid hard coding and make a dynamical read of the full map with links, modules, and etc. You can see that we have 13 modules, but it shows just 12 here with the different types of readout chips on them. Also, we have a single chip card. You might see on the bottom a small screenshot from my console, where I've been working straight with Apollo and checking up my test program. I still need to improve it a bit more. As an outcome, it would be a software component that reads information from the firmware and configures modules. My next steps are to work on calibration routines with the readout chips, such as pixel alive calibration, noise scan, and threshold minimization, and so on. I think that's all. Thank you for your attention. Right.
Thank you. Any questions? Okay, thanks. Egle?
Yes, hello. I'll show my screen. Can you see?
Yeah, I can see it now.
All right. Okay. So, hello everyone, my name is Egle, and my IRIS-HEP project is adapting the Coffea framework for FCC. A little bit about myself is I have bachelor's in physics. I just finished this year and I am starting my master's in September. I'm from Vilnius University and previously worked on a trillion study using CERN CMS Open Data. And my mentors right now are David Lange and Prayak Yadav. The Future Circular Collider is a proposed next-generation particle accelerator at CERN. It aims to reach up to 100 tera-electron-volt collision energies, significantly higher than the LHC. With greater precision and data rates, the FCC could open the door to a deeper understanding of the standard model and potentially uncover new physics. Even though the FCC is not to start running for the next 15 to 20 years, it is crucial to develop robust data analysis infrastructure now to ensure good preparation for when the real data begins to flow. The Coffea stands for the Columnar Object Framework for Effective Analysis. It's a Python-based toolkit designed to streamline data analysis in high-energy physics. Coffea simplifies workflows and improves reproducibility, making it ideal for analyzing large data sets like those expected from FCC. Coffea has already been successfully deployed in CMS, Compact One Solenoid. However, its application to FCC data, which is based on Key4HEP and FCC-specific software ecosystem, is still being developed. This will allow for Coffea to work smoothly and be compatible with the data formats and workflows used in FCC environment. One key application I looked into was the ZH production channel, where both the Z and the Higgs boson decay into leptons. This clean 4-lepton final state makes it a useful benchmark for FCC analysis using Coffea. And as we can see from the graph, it shows results accurately. We can see the Higgs boson peak at 125 GeV. My goal for this project is to build documented examples showing how FCC simulated data can be analyzed using Coffea. This also means ensuring compatibility with FCC software tools like Key4HEP and FCC SW. So far, I've spent time learning key libraries like NumPy and Awkward Array and Coffea, and reviewing existing coffee-based analysis and successfully running and fixing those codes because I ran into some errors while trying to do that. So I've now successfully set up the environment for running coffee-based FCC analysis codes. And going forward, I'll focus on developing my own analysis examples using Coffee, tailored for the FCC environment. Thank you. That's about it from me.
Oh, thank you. Alex, you have a question?
Yeah, thanks for this talk. This is a cool project. I'm wondering, the files that you're using here, I mean, you showed this plot already. Is the format of the data standardized in some way where kind of everything looks the same? This is a very naive question because since this project is kind of far into the future, I don't know how, if everything looks the same or different people working on it all have their own kind of formats. So is it standardized and it's kind of simple to use lots of different files, or is there a lot of work that you have to do to make them all look similar enough that you can work with them in your code in some way that is consistent?
So far, this is not my plot that I'm showing. It's just from one of the analyses that I reviewed and analyzed, so I could go forward and create my own.
Alex,
Okay,
I can
so
help
that's
out.
something.
It's yeah, there's this standardized but evolving set of data formats. The jargon is EDM for HEP format. It's not simple to use, so it's C++ classes, not columns, but we're making it look like columns via Awkward and Coffee.
Okay, right. So then that's very nice because that means anyone coming along wanting to use that data probably will have a much easier time with Coffee then at the end if you shape the data in a way that looks more uniform. Very nice. Thanks.
Okay. Any other questions? Okay. Up next is Kyrylo.
Yeah, hello everyone.
Hello.
Do you see my screen?
Yes.
Okay, cool. Let's start. So, hello, my name is Kyrylo Filonenko. I'm from Taras Shevchenko Kyiv National University. And my mentor is Valeria Lukashenko. She's from University of Zurich. Theme of my work is tagging low momentum tools in CMS. So what's about me? I'm second year master student. My field is high energy physics. And interesting fact, I love like physics, going to meetings with famous people from different fields, such as economics, maybe human searchers or something like that, and watching the audience reaction when I say that I'm studying at the Department of Nuclear Physics. It's very interesting and funny. So let's go back to my project. I doing my work on CMS. It's not content management system. It's a big experiment on LHC in Geneva. So what its research goal is Higgs boson and its properties test the standard model and also studies beyond the standard model. It is dark matter, extra dimensions, and many others. So it's interesting and cool experiment. So its detection methods are precision silicon tracking for charged particles, also colorimetry for photons and hadrons, and dedicated muon system, always an 40 superconducting solenoid. So my work connected to tau lepton. So why is it interesting and I need to do it? Okay, because Flavor puzzle is like one of the most interesting and non-studied question in
Я выступил.
Luka, you turn on your micro. Okay, yeah, thank you. So it's one of the most interesting and complicated questions in particle physics in standard model, and from like electron, muon, and tau. Tau is the least studied lepton, so it's the most interesting, especially in Bemezon decays. We have like the lowest amount of information. Also, this is sensitive to new physics, motivated by anomalies in RD and RD star. So what is the main challenge is standard hadronic tau reconstruction loses efficiency for momentum lower than 20 giga-electron-volt. And this study focuses on low momentum tau, so lower than 10 GeV. So we need specialized tagging methods. Like what is my project goal? It is develop and dedicated tau reconstruction algorithm for CMS round 3 and extended low PT 3-prong tau tagger using ABCNet. So in LHC, there are a lot of information after collision, and we need to distinguish our decay from that amount of background. So now we use like machine learning for this, and because people by hand can't do it, or it's very difficult and take a lot of time. So we'll use machine learning for this, like a benchmark process for starting taus is B0 decay, and like for run 3 adaptation, we'll handle higher pileup and increase event complexity compared to run 2. So we increase background and it's starts distinguish our decay like harder and harder. What we will use, I'll train my ABCNet based tau tracker with run 3 data using our benchmark. So there is ABCNet, but it is for muon decays and run 2, and I need to adapt it for taus and run 3. Also explore alternative machine learning methods such as particle transformers or others, like to search better performance. So I use Python, TensorFlow, and maybe some supporting libraries for model training. And also I'll implement robust training, validation, and testing pileups for ML-based tau tagging. Thank you for your attention.
Thank you. Any questions for Kyrylo? No? Okay. Up next is Patrikas.
Can you see my screen?
Yes, we can see it. Can you speak up a little bit?
Yeah, then I'll
Okay.
try to speak louder. I don't
Yeah,
have...
that's fine. That's good. Where you're at.
Okay, great. So I'm doing backend update of the AlCaVal framework for validation of and calibration and aligning conditions. So I'm from Vilnius University. A little bit about me: I finished software engineering bachelor's, and I'm currently studying masters of deep tech entrepreneurship. Yeah, these are my mentors, and what I'm doing here is AlCaVal framework update. So basically, AlCaVal is alignment and calibration validation framework for the CMS detector. Basically, conditions at the detector change, so we have to adjust the received data by some value, and we have to validate that value that we change the received data by in workflows. And these workflows have tons of different statuses. So basically, current problems are that there's not much insights into statistics of the workflows, how quickly they change the status, are there any bottlenecks? Also, slow pipelines of validation, no automatic conditions workflow refresh. So if there's some status, we have to manually, we used to have to manually press update buttons and to request for update of those workflows. And the problems will be solved by having a dashboard for those statistics, how quickly each transition between statuses takes, and how many are of those transitions, and optimization of the pipelines, so automatic refresh of workflow statuses, and informing the user, or in this case, AlCa service user, if there's a workflow that has already completed. So my first task I've already done, and it's in dev environment. It's this dashboard, so we can see what sort of how it looks like, what those transitions that I mentioned, how long they take, and how many of them there are. Yeah, and it can be filtered by batch. So if it's like CMS in general, if there's like some batch that's more specific, I can't remember the detector names off the top of my head, but the data can be shown by all time, last 90 days, last 30 days, last 7 days. I can adjust it a little bit according to input from my mentors, but so far this works. And my second task, it's not currently in dev environment, it's only in PR, but I've adjusted so that there is automatic refresh because we use an external API to get those statuses into our database. So this runs on I didn't mention, the dashboards run on a 15-minute job where it refreshes this like calculated aggregated data from our database every 15 minutes, and saves into a temporary file in the Docker container that this app runs on. And this also, the auto refresh and email sending also runs on a 15-minute job that it requests, it fetches data from the database and compares it to what's received from that external API. And if there are any changes, it saves those changes and notifies if there are any relevant workflows that are complete. So that's it.
Thank you, Patrikas. Any questions? Okay. Up next is Roman. Roman K. Oh, there you are. Sorry.
Yes, so my project is developing a Pythonic tool for smoothing histogram. My name is Roman. My mentors are Muhammad Ali, Alexander Heltait, Matthew Fakert. I am from Priazovsky State Technical University. I have a bachelor degree in applied mathematics. So, why it's so important? So, large hadronic collider analysis use histograms for their analysis, but to extract more useful information, we apply different smoothing algorithms to try and get more information from histograms. So the problem that existing tools they don't have a very accessible interface to user. They don't integrate with scikit-HEP ecosystem, and there's very little tools like this. So our goal is to implement Python tool for it integrated in scikit-HEP system with user-friendly interface, and additionally evaluate algorithms how good are they for your histograms. So right now we implement two algorithms. First is proposed by Twiki. You can see right now actions that codified by numbers and letters. So if we have number, we should apply moving median to our data. If we have letters, we apply Hanning, quadratic interpolations, and so on. Additionally, we have twisting operation. It's when we distract from original data our smooth data, apply to, it's called residual, and we apply to it our smoothing algorithm again and add it to our smoothing data. So from these single operations, we combine them into some algorithm. As you can see, here is some recommended algorithms combination from different sources. And second algorithm is rebinding. There is monotonic and parabolic versions. So we merge bins, the most compatible between each other until we have only two for monotonic or three for parabolic extremum. Then we rebind until uncertainty smaller than 5% in all bins. Here is visualization result. We additionally implement grid visualization function where you can specify your distribution that you want to plot, your bins that you want to test, and algorithms that you want to test. So here you can see one distribution on different number of bins. We apply two algorithms, you can see here, and on the legend we evaluate p-value from Kolmogorov-Smirnov test and reduced chi-square value, mean ratio value. Additionally, we plot ratio plot, and here is example of different distributions, two different here. They originally one under another, but I split it so you can see it. And right now we packaging everything in the working library. It's all. Thank you for your attention.
Thank you, Roman. Any questions for Roman? No. Okay. Up next is Cody.
All right, can you see my screen?
Yes.
All right, so my project is differentiable modeling of systematic uncertainties in Alice object corrections. I'm Cody Tanner, and my mentor is Gordon Watts. We're both at the University of Washington. So a little bit about me. I'm a third-year student at the University of Washington, majoring in physics and astronomy. And in my free time, I like to play soccer, go backpacking, and climb mountains. So the motivation and goals for this project. So the current Atlas object corrections use histogram lookups and conditional logic. And these methods are both non-differentiable and computationally expensive. So they're slow to evaluate at scale, and they won't work in gradient-based workflows because conditional logic is non-differentiable. And so our goal here is to build a neural network, which would of course be differentiable, which would replicate the Atlas corrections and their systematic variations. This would be differentiable, fast, and easy to integrate in full analysis. So our main objectives would be to learn a function f of, for instance, the pt, the transverse momentum. And this would be a function of the uncorrected momentum and x. And x would be some training parameter that we need to find. And it could contain many different parameters. And a sub-goal of this project is to find the dependence of the different components of x. So how much does each parameter matter? And so some examples of some parameters in x would be the number of primary vertices or the number of muons in an event. So where are we now? Well, we have a model that performs with around 3.6% error, predicting px, py, and pz. And we can see the histograms on the side showing their distributions. And we're looking into different loss functions and architectures of this neural network. We're trying to reach around 1% error. So we still have a little ways to go, but we're just adding on different parameters in X and the error goes down. And in the future, we'd like to build uncertainty into the inputs. We haven't done that yet. We're still trying to get to that 1% error before we do. But once we build uncertainty inputs, then the model will be able to predict more things. And in the future, we'd also, given time, like to expand this beyond just the data set that we're working on right now into more Monte Carlo simulations. So thank you. Yeah, Alex, you have a question?
Hey, yeah, this is an interesting idea. So I wanted to make sure I understand the setup correctly. In these figures where you're predicting the kinematics, is it that you have some nominal distribution for these kinematics and you're trying to predict the kinematics under some systematic variation? Or what's the input that you're starting off from to do your prediction?
So we're starting off with the uncorrected kinematics, so just from the simulations, and then we're trying to correct it to the true kinematics.
Okay, so you're learning the correction effectively.
Yeah, exactly.
Okay, yeah, I see. Cool, thanks.
Any other questions?
Thank you, Cody. Next up is Svitlana.
I hope everyone see my screen.
Yep.
Okay, perfect. Hi, my name is Svitlana and I'm on Princeton University. My project is RECAST-like workflow for analysis grand challenge Coffea implementation. My mentors is Alex Held, Oksana Shadura, and Palabidas. I'm currently a graduate student and I'm preparing for PhD. Our main goal is to build a modular analysis pipeline that make it easy to repeat studies and test new hypotheses. Actually, that is why we use Rihanna, because Rihanna allows us to run the entire workflow with a single command. And it uses containers to create the same analysis environment everywhere. For example, we can create it on Kubernetes. AGC defines each step of the analysis from processing single files to creating final histograms. Actually, my work is based on the Coffea workflow, which was inherited from previous followers. A little bit about our structure. Actually, Rihanna supports snake-make workflows, and our analysis use two-level parallelization strategy to ensure optimal performance. And here you can see the structure of the analysis. We start with a JSON file that listed the nano-AAD inputs files, and each file is processed in parallel. This is a skytable step, and when we merge files per sample. In the final step, we create our full histograms, and each step is cached, so it doesn't have to run again. And this is very important for our RECAST-like approach. Actually, what does RECAST-like mean? It means we don't have to process everything again if we want to test a new signal. We can just replace the signal sample or our TRL model. For example, if we added new signal, we run only the final analysis step. And thanks for RECAST, we can reuse all intermediate files and focus only on the changes. This makes it easy to test many different models much quicker than if we will run it again and again. Actually, we cannot use RECAST in original form. It's more for Atlas, so we use a similar implementation. About my current progress, so far we have deployed the Rihanna infrastructure. We added some new simulated signal, prepared JSON input file for 2016 data, also generate some histograms. And our new steps is to visualize spot fit prediction and create pool plots. Also apply a RECAST-like approach to analyze data and add some new nano-ID files to our analysis. That's all from my side. Thank you for your attention.
Thank you. Any questions for Svitlana? All right. Next up is Dmytro.
Yep, I'm here. Hello.
Okay.
Just a second. Okay, so sorry. Oh, okay, here we go. Do you see the presentation?
Yes.
Oh, wonderful. So, hello everyone, my name is Dmytro Belytskyi, and let me begin with a question. Why is it still so hard to use a published physics analysis for testing a new model? In this project, I'm trying to tackle the question by combining RIANA, SnakeMake, and AGC into a flexible reinterpretation pipeline. Our project is still a work in progress, but the main goal is clear. We want to make particle physics analyses more reproducible, modular, and scalable using RIANA. We're starting from the root analysis grand challenge, a realistic benchmark based on our data frame, and adapting it to a modern workflow-based setup. We're containerizing the entire pipeline so it can run independently in RIANA, and we're adding SnakeMake to handle parallel steps more efficiently. We will also change the analysis code to take a single file, which makes things easier to manage and reuse. Looking ahead, we wanna support the reinterpretation of new physics models, similar to RECAST, and automate the full chain from CMS open data to final results. This is the full root AGC analysis, a realistic example of how CMS-style workflows operate. It starts with nano AOD files which already contain selected physics objects like jets, leptons, and matter. The analysis goes through several stages, selecting interesting events, computing features, training a machine learning model, applying it to data, and finally performing statistical inference. It's a complete end-to-end pipeline. Our goal is to take this complex setup and turn it into something modular, reproducible, and workflow-ready in RIANA, so that anyone can rerun or adapt the analysis with minimal effort. One of the big challenges in this kind of analysis is managing all the moving parts. We often want to run the same code on many input files or generate results for different physics models, and we want all of that happen in parallel, efficiently, and reliably. To make this work, we're using SnakeMake. It let us describe each step as a rule with clear inputs, outputs, and comments. Then it builds a workflow graph and runs everything in the right order, using all available resources. We define everything through a JSON config file, and from that, SnakeMake creates the full set of jobs. This makes the process faster, more organized, and much easier to reproduce. One of our long-term goals is to support reinterpretation similar to what RECAST processes. In particle physics, it's often hard to reuse an existing analysis to test a new model, even if all the code is available. But with workflow tools like RIANA and SnakeMake, we can make that easier. Our idea is to separate the physics model from the analysis logic. So instead of rewriting code, a user could just provide a new configuration file with the signal processes, selection cards, labels, and input data, and the workflow would run automatically. This could eventually let researchers test new scenarios without touching the core code. Here's where we are so far. The Rihanna setup is done and working, and we've successfully processed 2015 CMS Nano AOD data. We added a simulated signal as a prime decay into top quarks, so we can explore beyond the standard model. We also modified the AGC analysis to accept a single file and automated the generations of those configs. The pipeline can now produce histograms, and we've already prepared inputs for the 2016 data. Next up, we plan to add post-fit plots, extend the reinterpretation features, and automate the production of nano AODs directly from CMS open data. And that's all.
Thank you, Dmytro. Any questions for Dmytro? No? Oh, thanks again. Devon?
Yes. Okay, so my topic is accelerated HL-LHC particle track reconstruction methods with myself, Devin Bontrager, and my mentor, Liv Page. Quick about me, just an undergrad at the University of Kansas studying engineering physics. The GitHub's linked there. On the right are a couple organizations I take part in my university. The project GitHub is down below. So why this matters? The challenge is in the HL-LHC environment. Track detectors today will have high collision rates, flooding the reconstruction pipelines with dense hits. And we want a faster, smarter way to build the tracks, which are not always obvious, by having lower compute times and focusing effort where it counts. So the end goal is to create a framework that allows the track collaboration while growing branches, and also using typical maze solving algorithms and adapting them to this use case to see if they may have some merit. How we build tracks. So we start with inner seeds, and we expand each hypothesis or seed using a Kalman filter. We keep the top candidates for each seed and prune lower candidates if they exceed budget. And then finally pick the highest ranking full-length tracks and go over and refine. While this struggles a high pileup, though, dense hits have a bunch of near duplicate hypotheses, and it waits until candidate lists overflow, meaning you have wasted computed time because you're computing the same thing, and there's a bunch of time efficiency bottlenecks. Like a lot of the time, most architectures run the building for each track one after the other and not in parallel, and then a rising fake rate, which is just increased wrong hit assignments, lowering overall purity. So our approach is to parallelize the track building, but not just in running them all at the same time, but also letting each track hypothesis share a quick score with other tracks while constructing, eliminating options for each other based off of their branch scores, This removes the duplicate track reconstruction, as well as helping fit those tracks better earlier on without needing more refinement after the case. Also developing a brancher toolkit, which uses the methods listed, which are just typical maze solving algorithms, as the branchers instead of just doing it randomly and splitting off into 5 or whatever different branching at each node, I guess, or hit. Just to test if one outdoes the standard. So what's done, already a replication of baseline in a Python environment just to get the grasp of it, as well as just a robust environment for all of the algorithms. So as well as what's done is all 6 algorithms, and what's in progress is the parallelized track building and adding track evaluation metrics. There are some track evaluation metrics, but we're going to add some more as well. Any questions?
Any questions for Devin? All right, thank you, Devin. Up next is Yuri.
Hello, everyone. Okay, let me share the screen. Okay, you should see it. And now we should see it in presentation mode, right?
Yep.
Okay, hello, everyone. My name is Yuri Perets. I'm Bachelor Studies graduate from Kyiv National University of Taras Shevchenko. Team of my project is CMS for calorimeter run-free data analysis. My mentors are Alexey Shavelov and Lenkaityte. You can see on the screen a few logos here: Brill project, and CMS experiment. So let me introduce to you what are we working with. So Brill project, or the beam radiation project, as you may assume, focuses on the luminosity measurements and the beam instrumentation measurements. Project is responsible for a large number of detector systems, but in our project, we will focus on the forward hadron calorimeter, which provides luminosity measurement for the CMS experiment and has 2 counting algorithms. First one is the HF occupancy method. It's based on 0 counting, so we are tracking the fraction of bunch crossings with no energy depositions above some threshold. The second one is HF transverse energy method. Is based on the assumption that the measured transverse energy sum is proportional to the luminosity. And both of our methods require corrections to account for out-of-time signals, also called as afterglow effects. So we have 2 types of such effects. Type 1 afterglow effects contributions are due to signals that originate from the previous bunch crossings, such as the spillover of electronic signal. And type 2 afterglow effect arises from the activation of surrounding detector material by a colliding bunch, so resulting in an exponential decaying signal over many subsequent bunch crossings. Another possible source of error is also called as a pedestal. It is a constant electronic noise offset that biases the energy measurement. And you can see on the graph why is it called pedestal. Also, you can see on this graph, here's our colliding bunches. With the blue dots, you can see uncorrected data, our observed data that we can see from the experiment. And with the red crosses, you can see our corrected data. And as you can see on the graph, even at the non-colliding bunches, even at the empty bunch crossings, there are still some luminosity registered. And after correction, you can see correction results in 15 to 20% of correction from like the maximum value of luminosity. So it is a very large number. So our main focus is to measure both types of out-of-time response and estimate the pedestal. The algorithm used to estimate afterglow type 2 afterglow type 2 effects is called single bunch response. Model assumes as a first approximation that the induced signal is always proportional to the luminosity of the individual colliding bunch. You can see on the graph here with the red star is our colliding bunch. Then you can see afterglow type 1 effect. And here you can see afterglow type 2 effect. So it is exponentially like decaying. Okay, and this single batch response is very important because we even have we even have runs on the experiment with a low number of bunches, so you can better estimate this error, this bias. So what we will do in our project? We are using the toy Monte Carlo method. If we want to validate if our single bunch response model is like the best possible, we want to validate is maybe there's something better, or yeah. We want to simulate different thinning scheme patterns with Prandtl luminosity and estimate the influence of pedestals, type 1 afterglow, influence of type 1 afterglow, and their possible drift during the year. And after a better understanding of these simulations, we can try to improve the correction physics data. Corrections would be applied to the full year of data as part of the project. And final product of the project will be the framework which allows offline application of the corrections and data reprocessing. Thank you for your attention. Any questions?
Thank you, Yuri. Any questions for Yuri? Okay, next up is Ivan.
Hi.
Hello?
Can you see it?
Yeah.
Can you hear me?
Yes. Yes, we
Okay.
can see and hear you.
Good afternoon, everyone. I'm Andreevsky Ivan, IRIS-HEP fellow from Taras Shevchenko National University of Kyiv. I'm second year master in high energy physics. This summer I'm working with Egle Belytskyi. I guess he is here. And Vladimir Bezguba on alpaca benchmarks for alpaca library. Let me start with what alpaca actually is. Alpaca is a header-only C++ abstraction layer for that lets you write one kernel and run it unchanged on CPUs, GPUs, or even FPGAs. No runtime, no language, just standard C++. The motivation is obvious to large experiments. We want to exploit heterogeneous hardware without cloning code for every vendor, and we want to stay future-proof when centers can swap architectures. CMS Pixel Track already uses alpaca in production in its backends. This year, developers are rewriting big parts of APIs alpaca into alpaca free. Before CMS or other user can migrate, we need solid performance regression tests across all backends. That's exactly my project. The result of work will consist of 4 parts. First, a set of big micro benchmarks that test the basic primitives of alpaca, starting with memory allocation, memory copy, and simple arithmetic kernels. This will allow me to familiarize myself with the library structure, library API, and as well as test the library itself, since it's still under development and maybe has bugs. Second, I need to write mini-build benchmark on Alpaca, and that basically this will be my main benchmark I have to write during this project. Third, each test is accompanied by catch-2 test and C-test targets, so that continuous integration can automatically pick them up. And finally, we will get an early performance dashboard that will tell CMS and other users whether it is safe to deploy Alpaca. The development environment is now ready. That's my current progress. Yeah, I'm creating it based on the latest Alpaca free branch using CMake and Catch2. The first benchmark memory allocation is complete. It lists all enabled backends, measures memory allocation time on the host and device, and outputs throughout metrics. The output formatting corresponds to Babel stream, so we can compare the same things. Babel stream is the only existing benchmark on Alpaca free, so I'm first repeating its structure and input-output style. CMake now register the test in CTest, sets number of bytes and runs flags, and all of this is located in the specific branch. The QR code takes you to the main Alpaca free repository if you're interested in it, where the benchmark may soon appear. And here is my fork project QR, where the benchmark code is already available. What's next? My memory allocation benchmark is currently undergoing code review. Based on the comments, I will continue writing micro benchmarks for memory copying and arithmetic. After completing this benchmark and agreeing on them, I will move on to the main benchmark of this project, mini-build. At the same time, I will write user documentation and possibly add GitHub Actions runner so that each pull request automatically receives a time. In summary, this test will ensure the protection of Alpaca free and assist in development and optimization of the library. The slides and code are available in the internet, and thanks for your attention.
Thank you, Ivan. Any questions for Ivan? Okay, moving on to the next one. Ruta?
Yes. Can you see the slides?
Yes.
Okay, so hello everyone, I'm Luka and my project is development of an LLM-based Copilot tool for CMS analysts. And my mentors are Peter Elmer, David Lange, and Gordon Watts. A little bit of my background. I am a physics bachelor student at Vilnius University. I had a side project learning about CMS analysis, particularly Trillian process, and I'm an IRIS-HEP fellow for 8 weeks. About the project background, as we all know, CMS data analysis involves complex specific tools which might not be that really accessible for beginners, and it takes a lot of time to search for documentation, and the existing documentation is fragmented through various sources. So what if analysts could ask a natural language question about a certain data set and get working code? Like, for example, how to plot the PT of the first 5,000 events in a certain date? So that's a really simple question. So to implement this LLM-based assistant, we can build a retrieval augmented generation RAG assistant. And why it is more efficient than fine-tuning? Because it's faster and uses less resources. And also it's easier to update with new documents. Also, I have written some CMS specific code hints, like the second picture. In essential, we just take a natural language query and try to return relevant code. And if it fails, we iterate through the code and the generation until it works. So a little about the workflow. First of all, we have some markdown files, the so-called hint files with Python code snippets, and we split them into chunks. Then we can embed them by section and store the vectors in a collection. Then the retrieval part, the user input is embedded and used to retrieve the top matching chunks. And finally, retrieved chunks are added to prompt, as well as they are combined and then passed to the LLM, which I'm using Llama 3 for that. And extracted code is executed, and retried if it fails. I meant to regenerate it. So that's the rough overview of the pipeline. So as mentioned before, we load the documents, then split them, and embed and store them into a collection. Then we retrieve the top matching chunks to the query, and then we use the LLM to generate code, and if it runs into an error, we retry to generate. So my current work is just improving the hint files. I'm adding comments and small edits to make existing hints more clear. Trying out more analysis questions to see what's missing from the hint files, and identifying what kind of hints are actually useful for code generation tasks. As far as I've noticed, this project relies on good documentation. And I think that's it. Thank you.
Thank you, Ruta. Any questions for Ruta? All right, and up next is Arvind.
Hi, can you guys hear me?
Yes.
Awesome. Let me just go ahead and share my screen. All right, you guys see the screen?
Yes.
All right, let me try the slideshow. Do you guys see the slideshow?
Yes.
Awesome. Okay, so hi, I'm Arvind Thakur. I'm working on developing modular ML pipeline templates for HEP applications. So a little bit about me. I just graduated with a double major in applied physics and computer science from UC Davis. And I'm on the 14-week fellowship with IRIS-HEP. I have previously held research positions in the physics realm, starting off with being a computer vision researcher under a professor at UC Davis, working on cosmology, sort of image fringe detection. The next one was as a data researcher at a condensed matter experiment lab, and then most recently under Professor Robin Erbacher, who some of you might know, working as a machine learning researcher. So the motivation behind this project is that in my latest position as a machine learning researcher, my onboarding time was quite long because the code base we were working with was very complex. And I later realized unnecessarily so. I found a lot of room for optimization and simplicity. And also, we were missing a lot of documentation. So I thought, given that machine learning is growing so much, and a lot of the code is very robust. You can refer to the machine learning, living review for that. But I think it is quite necessary to sort of have a go-to source for researchers to sort of look at templates or even, complete pipelines that they could use or inspire from. And that's what I'm making. And so what my project relies on are multi-branch repositories, which is essentially, we have a bunch of use cases for machine learning in HEP. I'm going to collect all of them in a manner I will introduce later, but each branch is going to correspond to a use case. And each sort of use case is going to be a sort of end-to-end pipeline. And every part of the pipeline is going to obey industry grade config management practices, experiment tracking, pre-commit hooks, hyperparameter tuning, and all of these are going to be taken from different frameworks already available to us. And the core ML algorithms are going to come from PyTorch Lightning because it's lightweight. And obviously, this is going to be HEP specific, given that we have a lot of libraries that we work with that are predominantly created for and by high energy physics researchers. We're going to make all of these machine learning pipelines very HEP specific. So what I've made so far is a proof of concept demo. Given that what I'm making is a framework, in order for it to work the way we want it to, which is installing it through pip, I'd have to publish it to PyPI. Since I haven't done that, I've made a local simulation of PyPI, which is basically a giant bash script. And so this is an example of me actually looking at a specific part of a pipeline that I've created, and I only want to import that. So what sets my project apart in this case would be you don't have to necessarily import an entire pipeline if you have an existing one and you want to sort of experiment with different machine learning techniques, for instance. You can import one of our sort of machine learning templates and you can choose where you want it imported to your local code base, and it's just going to be there. So even though you pip install it, it's not going to install to the Python packages folder in your desktop. It's going to be downloaded wherever you want it to. And so it's going to serve as a starting point for you, essentially. And so given that the scope of this project is so wide in terms of it addressing general ML research and HEP, I have drafted a pretty comprehensive survey that should only take you about 10 minutes. So if you guys could look at it and sort of maybe respond, it would give us a lot of insight into the ongoing research in machine learning and sort of pain points that you think could be addressed and room for optimization. So the next steps, well, the ones that I've completed so far are articulating the survey and then creating a basic proof of concept that I've just shown you. The next step would be to analyze responses from the survey and then fine-tune each use case based on it. And then the last step would be final touches, which would be very edge case addressing edge case scenarios that are very specific to sort of parts of the pipeline, and finally publishing to PyPI for all the researchers to use. That'll be all. Thank you.
Thank you, Arvind. Any questions for Arvind?
Well, the survey's also been linked on the chat. Anyone wants to start?
Oh yeah, and it's also, you posted it in the Slack general channel to IRIS-HEP. So.
Awesome, thank you.
All right, that's all we have for today. So thank you all for coming. Thank you to all the fellows for these interesting presentations. We look forward to seeing your final results. Thank you.